Hi there everyone. So now I'm going to just do a quick follow-up video here to go through some examples of orders of magnitude and SI units. And this will be a little less formal, so forgive me if I have to correct myself, and of course do remember to put in the comments if you spot any mistakes that I miss as we go through. So in this first screen, it says write these values as shown in the example. So here is the example, and if you think you can write these out now, then please go ahead and pause the video and have a go at that. But here, the first example is 200 eV, so that's small e, capital V, and these are electron volts, which are a real unit, although probably not one that many people have heard of. So if you have 200 electron volts, how will we rewrite that using orders of magnitude? And I've got this table over here, which we can see the orders like we saw in the previous videos. And we can see here that if we have 100 of something, so if there is 100 of some unit, then that would be 2 orders away from 1, so that will be 1 hecto unit. So 100 meters is 1 hectometer, and 100 electron volts will be 1 hectoelectron volt. But of course here we have 200 electron volts, so that means we have 2 hectoelectron volts. And you can see there that we write 2H, small h for hecto, and then EV is small e, capital V, because V for volts is a capital letter because there was a scientist called Volt. However, notice that when we write out the unit, it still has a small letter because the unit itself doesn't have a capital letter. The symbol we use for the unit is a capital letter. And in fact, when we write hectoelectron volts, we write it all as one word. In fact, up here, electron volts should be probably one word here as well. So that's the example. No strange units, or at least not too strange, as we go down the actual questions. And again, if you think you can do these now, then by all means pause the video and have a go yourself. So our first one, A, is 0.0059 volts. So which order of magnitude are we going to use? Again, if we look over at the table, there are 2 zeros after the decimal point, and that corresponds to this line here being minus 3 orders. So we take 1 and we divide by 10, divide by 10, divide by 10, we end up with 0.001, or 1,000th of 1. Okay, so here, if we had 0.01 units, then we would have 1 milli-unit. That's how that would work. But in this case, we have 0.0059 volts. So that will, in fact, be 5.9 millivolts. 5.9 millivolts. And I'm just going to write it out in full as well there. And again, notice that I'm not using a capital V when I write millivolts out as a word. I only use it for the symbol. So that's A. Moving on to B, we have 450 amperes. 450 amperes. So amperes, usually we just say amps. That's the common use. This is a unit of electrical current. So 450, we're looking at the same order of magnitude as our example. So instead of 200 electron volts, we have 450 amperes. So the only thing we have to do is make sure that we put the number after the decimal point. So we're in the hecto region again. If we had 100 amperes, then we would have 1 hectoampere. But because we have 450, that means we have 4.5 hectoamperes, or hectoamps. Okay, so that will be 4.5 hectoamps. And I'm just going to write amps there, although it amperes would be technically correct, and actually it should have this accent because ampere was French. So another thing we could do there, because we are down near to 1, we could make use of this first order of magnitude if we wanted to. It's 4.5 hectoamperes, but we could equally say that it is 45 decaamperes. And notice there, deca is the only one of these orders of magnitude which has 2 characters, dA, both lowercase, and then of course we have to put the capital A for amperes. So 45 decaamperes. So we could use different named orders of magnitudes for the same number. And you have to watch out when people use statistics. Usually they aim to use the one that makes the number fairly normal looking. But you can use an order of magnitude that makes your number look much bigger or much smaller than it is compared to other numbers nearby. So you have to watch out how people use numbers when they are writing out with these orders of magnitude. Moving on to C, this number is 56 million meters. 56 million meters. You're probably familiar with a million being 6 zeros. So there we go, 6 zeros. And of course, when we're writing out large numbers, it's traditional to, after each set of 3, moving from the decimal point, after each set of 3 digits, you put in a comma so that you can more easily see these orders of magnitude. So we have 1,000, million, billion, and so on. So 56 million meters. We can see there is a 1 million up there. So 1 million meters would be 1 megameter. And that means 56 million meters is going to be 56 megameters. And there we have to use a capital M for mega because that's the order that we are using, not milli this time. So this is 56 megameters. Now, if we wanted to use, let's say, a smaller order of magnitude, we don't have any names going down unless we go all the way down to kilo. And so if I wanted to say this was kilometers, we would have to say, well, this is 56,000 kilometers. So 56,000 kilometers is 56 megameters and kilometers. And there you can see very clearly that 56 megameters, well, it seems like a fairly normal number, is 56,000 kilometers, which seems like a much larger number when we look at it with our everyday viewpoint. So moving on to D, 0.0000672. So this is joules. Joules is the unit of energy. And if we look now, we've got 4 zeros before the first non-zero digit, and that doesn't correspond to any of our orders of magnitude. Here we've got milli, which is 2 zeros, and then micro, which is 5 zeros. So if there were 5 zeros, 1, 2, 3, 4, 5, and then the 1, this would be where we put our decimal point for micro, which is probably the best one to use. If we want to use milli, then we're still going to be having a number that is less than 1. This is fine. There's no reason why you can't write down a number less than 1, but it's often the case that we try to make our number more than 1. So this number would probably be normally written as 67.2 microjoules, and there is that Greek letter mu for micro there, so 67.2 microjoules. Now, if we were going to use milli, then we would only have 2 zeros before our decimal point. Oh, sorry, 2 zeros, and then we would jump over the 1 as well. So our decimal point would end up here. So it would end up being 0.0672 millijoules. So if we were going to write it as a number less than 0, it would be 0.0672 millijoules. Still a very small number, but not quite as small as the one that we had originally. So moving on to E, 730 and then 9 zeros. 9 zeros is a billion. So this is 730 billion pascals. Pascals is a unit of pressure. Now, 730 billion pascals, I don't think is a pressure that we will ever experience, certainly not on Earth. But billions are numbers that we deal with quite often. And if we look at our table up here, billion is 9 orders of magnitude away from 1, and the prefix for that order of magnitude is giga. So this is 730 gigapascals. So capital G, capital P, small a. Pascals uses 2 characters for its unit. So 730 gigapascals. Okay. Now then, if you are familiar, and you might be if you are using computers on a regular basis, the order above giga is tera. That is 12 orders from 1. That is corresponding to a trillion. So we could, if we wanted, write this as 0.73 terapascals, which is the next order up. And again, using a number less than 1, nothing wrong with that. So moving on to the last one for this section here, we have 0.000000008 ohms. Ohms is a unit of electrical resistance. And what we've done here, when you use big numbers, you traditionally separate each set of 3 orders of magnitude with a comma, starting from the decimal point. We often do something similar below 1, but we don't put those commas in when we are dealing with small numbers. There are some people who write out with a dot every 3 orders. Now, I don't like doing that because I think it gets confusing with the decimal point. But here we've got a number that is separated out by orders of 3 zeros just by a space. And that, again, just helps make it easier to look for how many orders of 10 you've got between the decimal point and your number. So we have 3, 6, 7, 8 zeros and then a digit. So if we look at our table up here, this last one is the longest one. 1, 2, 3, 4, 5, 6, 7, 8, and then a 1. That's perfect. So if we had 0.000000001 units, that would be equivalent to 1 nano unit. And so as we have 0.000000008 ohms, that is equivalent to 8 nano ohms. And again, nano is a small n, and then ohms is represented by another Greek letter. This is a capital omega. This is 8 nano ohms. We might hyphenate that just in order to make it clear, but that's nano ohms. And of course, we could rewrite it in terms of micro ohms if we wanted. It would be a very small number, or we could make it 8,000. What's the next one down? If I'm correct, I think the next one down is femto ohms. Am I right about that? You can go and check for yourself. That would be minus 12 orders. But we're not going to do that here. So that is the first set of examples. I'm now going to clear those away, and we'll move on to the other way around. So if we flip this around, where we now have the units and we need to write out the full number, how would we do that? So again, write these values as shown in the example. Here's our example. It's 45 MeV, so we're in electron volts again. And M, capital M, notice, Capital M corresponds to mega. Mega corresponds to 1 million. So it's 45 times 1 million electron volts. That is 45 mega electron volts, or 45 million volts. Okay? So that's what we're going to be doing. If you think you can do these questions, please, by all means, pause the video again and go ahead and do them. So this first one, A, is one that we are probably fairly familiar with, and that is 95 kilometers. 95 kilometers, so you probably know that 1 kilometer is 1,000 meters. If not, we can see that kilo up here corresponds to 3 orders of 10 away from 1, so that's times 10 times 10 times 10, which gets us to 1,000. So 95 kilometers is 95 times 1,000 meters, which equals, of course, 95,000 meters, okay, or 95 kilometers. And I think I'm going to stop writing out the full version of the word there, 95 kilometers. Careful, that looks a bit like 45. Okay. So next up we have, I think I've spotted a mistake here, we've got G5, big G, PA. Now this should be a large P because we are doing Pascal. So here, let me write that out again there, 5G, PA, like that. That's how that should look. And so what we're looking at here is 5 gigapascals, 5 gigapascals. I don't know why I'm so fixed on extremely high pressure in these examples, but we may remember from the last slide, giga, capital G, corresponds to a billion. So 5 gigapascals is going to be 5 times 1 billion. That's 9 zeros. 5 times 1 billion pascals, which is 5 billion pascals. So those were going up the table. The larger numbers generally are easier to identify, but now here we've got micrometers. Micrometers, 34 micrometers. Another way this word is said is micrometers. So micrometers or micrometers are the same thing. They are not different units. They're just different pronunciations of the same unit. So we have 34 micrometers, so that is 34 millionths of a meter. Micro is minus 6 orders of magnitude from 1. So plus 6 is mega, that's 1 million times, but minus 6 is a millionth. So if we had 1 millionth, then we would have 1 micrometer or 1 micro unit. But here we have 34. So 0.000001 is 1 micrometer. That's 1, 2, 3, 4, 5 zeros and then the 1. But that's just 1. We have 34. So that means we're actually going to use another order of magnitude closer to the decimal point. What does that mean? Well, that means it's going to be 34 times 0.000001 meters. And if we multiply this number by 34, then our answer is going to be 0.1234 zeros, then the 3, and then the 4. And that's going to be 0.000034 meters, 34 micrometers. And something similar is going on here with nanovolts in D, 460 nanovolts. So this is 460 times 0. And then 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 1 volts. So if we're doing 460 times this, well, 460 times 1 would be 460, using these 3 orders here, right? So our 460 is going to go above these digits in our final number, which means we're going to have 1, 2, 3, 4, 5, 6 zeros, and then we're going to write 460. So it's 0.3456460 volts. And technically, we don't actually need that last zero, because once we've got to the end of our non-zero digits, the others don't make a difference. Okay? So 460 nanovolts is 0.000000046 volts. And if we wanted to write that out using the separated zeros, we could do that. So we have two sets of 3 zeros and then 4, 6, 0 at the end. Well, that's a terrible looking 6. Sorry, I have to correct that. Okay. Not that my writing is particularly neat on this board. I hope that you can still make sense of it. Moving on to E now. We've got 87 megajoules. So we're back to the big orders here. We got big M, so that's mega. Now, you can hopefully by now fairly quickly move from saying mega, that's million. So 87 mega units is just 87 million units. So 87 million, I'm not even going to write it out in full, 87 million joules. And like I say, it is easier for the larger orders than it is for the smaller orders. The smaller orders where you have to think about the decimal points a little bit more carefully, you should be a little bit more careful with. But hopefully you are fairly confident with the big orders. And then finally, 6dA, and so small d, capital A, we're back to amps here. And notice that one small d corresponds to -1 orders. This is deci. Okay, now deca, which we saw +1 orders, is dA. We do have dA here, but remember one of those is our unit. Fortunately, we can see clearly that this big A is going to be the unit of amps or amperes. So that hopefully won't be too confusing, but you do need to be careful whether the letters are capital or lowercase. So 6 deciamperes is going to just be 6 divided by 10 once to go down to 0.6. So it's going to be 6 times 0.1 amps, which is going to be 0.6 amperes. That's going to be 6 deciamperes. Okay? So now we've gone from looking at the symbols and going back to the full numbers. So that is orders of magnitude. I'm going to clear those off now, and we're going to move on to standard form. So here are a bunch of numbers that we need to convert into standard form. And one thing that I didn't actually say in any of the videos is that there are two common ways that you will see standard form written. The one is what we looked at in the videos, which is times 10 to some power. But another one is to write it as having an exponent with an e. And I will show you those in the first one here. We've got, the first one is 5 billion. So 5 and then 9 zeros. So if this is 5 billion point 0, and we are going to move, we want to move the decimal pointer here so that we have a number between 1 and 10. So if we had our number 5, we would have to jump 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places to get back to 5 billion. So this number is 5 times 10 to the power of 9. So that is the way that we went through in the videos. But another way of writing this would be to say 5, and then you have an E, and then a 9. And some places use a small e like this. Some actually use a sort of a small size capital E instead. So the E, I believe, stands for exponent, but you have to be careful because, of course, it's not 5 exponent 9. 5 exponent 9 would just be 5 to the power of 9, which is a very different number. So if you want to write 5 to the 9, you can just write 5 to the 9, or sometimes 5 and then the little upwards pointing hatch arrow there and 9. So these are two ways of writing 5 to the power of 9, but that's not what we're doing here. We're using this notation E to stand in place of times 10 to the power of. So this is how we might write standard form, usually on calculators or anywhere which can't handle writing indices very well. If you can't write superscript numbers very well, then more often than not you're going to find it using this E notation. So that is A. Moving on to B now, this is 0.000000004. Okay, so we're going to start by making our number. If we put our decimal point after the first non-zero digit, our standard number is going to be 4, or 4.0 if you prefer. But to get back to our original number, we're going to be going left this time. And this is 1, 2, 3, 4, 5, 6, 7, 8 orders of magnitude. So obviously we're turning a small number into standard form, which means we're going to need negative exponents. So in standard form, this number is going to be 4 times 10 to the negative 8, or 4e minus 8, as it would be written in this alternate form, 4e minus 8. Okay. Next, we got 49 million. 49 million. So here you can see, now if we were writing using named orders of magnitude, we've got millions, that would just be mega. So we would have 49 mega units, whatever the unit is for this number. But when we do orders of magnitude in standard form, we can do them much more precisely. We can say, well, our first non-zero digit is 4, so we put our decimal point after that, and we get 4.9. And this is what I mean when I say you will always, if you do standard form according to the strict rules, have a number that is greater than 1 and less than 10, or it could be equal to 1, of course. So here we got 4.9. And if we want to get back, if we go from 4.9, we want to get back to 49 million, we have to jump 1, 2, 3, 4, 5, 6, 7 to get back to 49 million. So this is going to be 4.9 times 10 to the power of 7, or 4e, just going to do that one now, 4e7. Now then, it's perfectly okay mathematically if we were to say, well, 49 million is 6, so we could just say 49 times 10 to the power of 6. That's fine. From a mathematical point of view, the numbers are the same. But strictly speaking, standard form should use numbers between 1 and 10 so that you always have the correct number of orders of 10 shown after the multiplication. But a lot of people don't follow this rule correctly, strictly. Like I say, it's not wrong to write 49 times 10 to the power of 6, but it does just play a little bit fast and loose with the rules of standard form. So going to D now, we have how many zeros here? 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, 5, 6. So our standard number is going to be 5.6, you can see. And to get back to the original number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is what I said in the video about if you count the zeros, you count 9 zeros. But given that you're going to be starting from after the first non-zero digit, the actual number of orders of magnitude there is going to be 10. So this is going to be 5.6 times 10 to the power of minus 10. 5.6 6e minus 10. And I've just realized I didn't write 4.9 here, did I? Naughty, naughty. Okay, so this is 4.9e7. Okay, sorry. I made a mess of that, haven't I? Let's go back and just 4.9e7. Okay, so e, now we have 297, and then 1, 2, 3, 4 sets of 3 zeros. Now, 3 sets of 3 is a billion. Add another set of 3, and that is a trillion. So this number is 297 trillion. So if we were using named orders of magnitude, it could be 297 tera units. But here we're doing standard form. So it's going to be 2.97. And then we're going to be jumping, and we can count it. We don't need to count them individually. We're going to be jumping 3, 6, 9, 12, 13, 14 to get to our decimal point. And I'll just, in case you didn't follow that, I'm counting the sets of 3 and then the extra 2 here. But I'll double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And that gets us to 297 trillion point 0. So it's going to be 2.97 times 10 to the power of 14. 2.97 e14. Okay, and I think I'm going to stop writing the exponential form there now. I think you get the idea on that. Moving on to f. So now we've got a few more decimal points. And remember, we do need to write all of the non-zero digits. All of the non-zero digits are relevant as long as you need them for the accuracy that you are working out. So here, our standard number, we put the decimal point after the first non-zero digit, then there's a 0, but we still have non-zero digits after that. So our standard number is going to be 6.057. So 6.057, and if we want to get back to, now again, I haven't actually divided these up into 3s, but you can count them in 3s if you want. We're going to have to jump over 3, 6, 7, 8 numbers in order to get back to our original number, and that is going to be going from a small number, so it's going to be 6.057 times 10 to the power of minus 8. That's going to be what this number is. I'll just double check that. 1, 2, 3, 4, 5, 6, 7, 8. Go. And notice there I'm counting from the original number going right, or you can count from the standard number going left. The number that you count is what's important, and whether you're writing out a small number for giving negative exponents or a large number giving positive exponents, you actually just need to know that before you start. So here again, we've got 4,572 and then 12 zeros. So that's 4,572 trillion, or 4.5 quadrillion, which would be the next number up. But either way, if we put a decimal point after our first non-zero digit, our standard number is going to be 4.572. And then if we're going literally from here to here, so we can just count in 3s. 3, 6, 9, 12, 15. So this is going to be 4.572 times 10 to the power of 15. And once again, if you wanted to, there's nothing strictly wrong with saying it's actually 4,572 times 10 to the power of 12. But now you're kind of making it look like a smaller number. And if somebody's not careful to notice that this is actually a comma, whereas this is actually a decimal point, you could actually mislead a person as to how big your number is. Now, that would be their mistake, of course, but that's why the rule says use standard form by making a number that is greater than or equal to 1 and less than 10. And that way everybody knows if it's in standard form, you're looking mostly at the order of 10 to know how big or small the number is. Okay. So now here at H, we've got a slightly longer string of non-zero decimals, and we have 1, 2, 3, 4 zeros, then a 1, then 2 zeros, then 8, 5, 6, 3. So our standard number is going to be 1.008563. Now, doesn't matter that these numbers are 8, 5, 6, 3, and this is only 1. This 1 is 1,000 times bigger than this 8. We are 3 orders of magnitude here. So this 1 is by far the biggest part of this number, and it's the first non-zero digit. So that's where we put our decimal point. And so we're only counting 1, 2, 3, 4, 5 to get to where we place our decimal point. So this is going to be 1.008563 times 10 to the power of minus 5. Now then, because the 8, 5, 6, and 3 are so much smaller than the 1 in this case, you might, depending on what you're doing, you might say, well, this is essentially equal, approximately equal to 1 times 10 to the power of minus 5. And in some situations, that might not matter. It might be quite okay to say this is 1 times 10 to the minus 5. In other situations, you might need those extra decimal places. They might be extremely important. So just be aware of how accurate your numbers need to be. And if you're not sure, try and include as many decimal places as you can. So in I, we have another long, small number. And again, I haven't divided them up into threes, but obviously there's only a single 6 at the end. So it's going to be 6, but 6 times 10 to the power of what? So we're going to have to jump over from here. Let's count back the other way this time. 3, 6, 9, 12, 14, 15, 18, 19, 20. We're going to have to count back over 20 digits to get back to the decimal point where it started. So this is going to be 6 times 10 to the power of minus 20. Okay, and now for J, we have a similar big number here, but we start off with 1 point, to put the decimal point after the first non-zero digit, 30567. And this is 1, and then how many sets of 3, 3, 6, 9, 12, 15, 18. So this is 1.30567 times 10 to the power of 18. And then in K, we have another big number, but now every single one of these digits is non-zero. Doesn't matter, we deal with it in the same way. 1, and then that's the first non-zero digit, reading from the left. So we have 1.3471256365428. That's going to be our standard number. Now, in most situations, we do not need all of those numbers. So in most situations, you are going to round up at some point. And that's what I'm going to do here. So this number is going to be approximately equal to, so this is approximately equal to 1.347, and that's where I think I'll stop, because our next digit is a 1. So there's only a very little bit added on there. So it's relatively close to 1.347 times how many? But we still need to count all of these orders of magnitude, because remember this number is going to be 0.0 here. So we're still going to be counting, let's see, 3, 6, 9, 12, 13, 14. So it's 1.347 times 10 to the power of 14. Now, like I say, technically it's 1.347125636542887 times 10 to the power of 14. But in most situations, you're not going to need all of those digits, even if you are counting. If this was a number of people, for example, if this is how many people live, well, this is far more people than live on the world, but if this was a number of people, you wouldn't want to say, oh, there are exactly this many people. You would say, well, there is in the order of 134 trillion people, if you wanted, or 1.347 times 10 to the power of 14 people. And that would be as far as you would probably need to go if you were dealing with that. If you're dealing with something extremely precise, then you might be more careful and you might need to include more decimal points. And finally, we got this epically long, small number here, 0. I'm not going to try and count them, but whatever it is, our standard number at the end is going to be 4.56. So it's going to be 4.56 times 10 to the power of what? So if we are counting from 4.56, we're going to be going back 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 34. We're going to be jumping over 34 orders of magnitude to get that decimal point move. So this last one is going to be 4.56 times 10 to the power. Whoops! Did anyone see the mistake? This is a small number. So this is going to be not 4.56 times 10 to the power of 34, but 4.56 times 10 to the power of minus 34. And you do really need to be careful with negatives in all sorts of places in maths. They can really mess you up if you miss one, but especially in standard form, because that was almost a very, very big number and not a very, very small number. So there are some examples of how we do orders of magnitude and standard form. I hope you found that cleared up some of your problems. I hope you were able to read my not great writing. And please go off and try and do some more practice for yourself, because watching and understanding a video is great, but you don't fully internalize your understanding until you do it for yourself. So please go off and try and do some of these for yourself as well. Thanks very much, and bye-bye for now.